Well, 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 you all survived the polar vortex that is the current storm. You also survived this morning, so congratulations. Can't say the same for my Honda Civic. It's been skidding all morning. But we're all here, so very happy to have you all here. As you can tell from today, we're doing a demo, and I may or may not have hinted at that, in my announcements anyway. Let me project and see how we're doing on resolution. I think, let me see. Box input. Okay, so it's a little bit below. Okay, here we go. So this is the background. I will also post this in the demos section of Carmen once I pull this out of the way. Okay, so we'll talk about the Kirkendall effect, which is the diffusion of two metals together, or actually any particular system, but the famous 1942 publication by Kirkendall was based on this, which is the understanding of atoms and metals up until that point was that you have an interchange. One site, a metal A goes to metal B site, and then you have the flux going the other way. Okay, so that was the understanding, in that the rate of exchange was equal. What Kirkendall said was that it's not equal, right? The flux of one atom, of a particular system, here it's copper, going one direction, is not the same as that of the flux of, let's say, zinc, or the second atom going in the opposite direction. And this was huge. I mean, at the time, I mean, we all take it for granted because it's now in our books, it's widely accepted. But in 1942, Kirkendall had a very hard time convincing his peers, his scientific peers, that this was correct. He repeated his experiments. His PhD student, Alice Smilkogas, I could never really pronounce that name, so I apologize to her. But they did these experiments over and over again, and they proved if you put an inner wire in the middle, right at the interface, usually it's drawn as a dotted line, but these wires that are coming in and out of the plane, if you then track the two atoms diffusing against each other, the inner layer does not change. So you see contraction on one side, which means the flux is increasing, and then it's going faster, and then you see expansion on another side. Okay, so all that is to say is that the two fluxes are not the same. And that was not widely accepted. I mean, it became accepted. The paper that was submitted, I think, in 42 was finally published, in 47 or something like a few years later. So I share this story because, if you're doing your science right, you're being rigorous about it, and what you're doing is physically, possible, and that you're not, just changing something that you don't know or something like that. If you're doing very rigorous experiments and you believe in your science, you have to be able to defend your science, because even senior people sometimes go by the rules that have been established for a long time. But if you have a new idea and it's grounded in theory, it's grounded in your repeated experiments, you have to stand there and defend your work. You also should listen to critique. That's not to say just because you're right that you're always right, but it's a dialogue. Science is ever evolving. That was an example from the 40s. So you think, well, instruments were not that great back then, maybe that's a lot of argument. No, I mean, these stories have persisted through time. There's a great example in the 80s of Nobel laureate Dan Shechtman. We're getting away from diffusion now, but we're getting back to crystallography. So Dan Shechtman saw in transmission electron microscopy this alloy that had 5-fold symmetry. Now, we haven't gone over 5-fold symmetry in crystallography. We've gone over 6-fold symmetry, 3-fold symmetry, cubic systems, right? We've gone over 4-fold symmetry. We haven't gone over 5-fold symmetry because it's actually not possible unless there's local disorder. And we talked about local defects, things like that. But it was revolutionary when Dan Shechtman saw this in the TM. He's like, oh my God, the diffraction pattern says it's 5-fold. And if you ever look in his lab notebook, all he wrote was 5! And that was the Nobel Prize winning discovery. And for the longest time, the big names of very established people, such as Linus Pauling, he wasn't the only one, but he was a huge name, and we've come across his name before, who didn't believe it, because 5-fold symmetry is impossible to propagate in long-range ordering. Okay, if you've ever tessellated, 3-fold symmetry in hexagonal HCP crystal structures, you can see 60 degrees, you go around, it makes 360, everything's peachy. 5-fold can exist locally. And then recently, I think in the 90s, they found this in this mineral that existed in nature, somewhere in Russia. But they found it, it actually exists. The alloy that he worked on was made in the lab. But in '82, when he submitted this paper to PhysRev B, Physical Review B, he also was rejected, and he was called a number of names that were not professional. Okay, so it's okay to have an argument. It's okay to sit down and have real discussions with somebody and say, I don't understand what's happening. I've never seen this. Where's your data? How many times did you repeat it? What were the conditions? You can have real discussions like that. And if it's new and people haven't seen it before, you may come up against such resistance. But Dan Shechtman also really stood firm to that. Actually, I should be stirring this while I talk to you all. Okay. And I should also be wearing gloves. So anyway, Dan Shechtman, stuck to his guns and really persisted for 2 years before his paper was actually accepted. And so in '84, it finally got published, and then in 2011, he shared the Nobel Prize for quasicrystals. So anyway, those are just two sorts, and that's a more recent example. So what I'm doing here is not stirring correctly. Okay, there you go. So what I'm doing here is actually just stirring in some zinc sulfate. So as Kevin said, you dissolve something in something, right? So what this something is zinc sulfate in just water. What I've done previously also is collected some of your pennies. So thank you for donating your pennies, folks. And if you look at pennies from, actually if you just look at the Wikipedia page of pennies, you'll see that before 1982, there's actually a lot of them. It's not just 1982, it's not the special marker. But before 1982, coppers were made mostly of pennies, about 95%, and then 5% zinc. And then after 1982, 1983 and on, there were 97.5% zinc, and then 2.5% thin layer of copper on top, mainly because the price of copper went up, and so they just switched the composition. When you mix the two, you get something that looks like this. It's a little bit yellowish. I don't know if anybody back there can see that. So let me switch. Okay, so what's really cool about the Kirkendall effect is that it not only occurs in the bulk, but it occurs at the nanoscale as well. So people have taken advantage of this more recently in the early 2000s to design some pretty cool morphologies for a variety of applications in either catalysis or for environmental remedial applications. So what people have looked at is either copper and oxygen. So you remember the discussion of in the recorded lecture that in a ceramic system, right, the cation would diffuse at a different rate than the anion. And typically the smaller cation will diffuse more quickly than that of the oxide, right? So you have copper oxide or nickel oxide, the cation, the copper 2+ or the copper plus or the nickel 2+ will diffuse in one direction at a different rate than oxygen going in the opposite direction, okay? And then the other thing to think about in terms of the Kirkendall effect is that not only do you have the diffusion rates of the flow rates of the atoms themselves of copper and zinc, but you also have to remember that there are vacancies that are hopping back and forth, right? So we've talked about how atoms can hop from one site to another via vacancy diffusion or interstitial diffusion, and we can calculate these rates. Well, if an atom is moving this way and it's hopping into a vacant site, that means the vacancy has to go in the opposite direction at the same rate, okay? So vacancies have to move as well. So that's what you see here. This is just a generic example, not particular to copper and zinc, but you could see if you have some element A and some element B, the fluxes, or J, are not even. And so to compensate for that, there's also a vacancy diffusion, right? Just because it's not a physical atom doesn't mean it doesn't have a rate. And so because of that, because of the uneven flow rates, what you get is this pitting. You have a buildup of these vacancies, of these voids right at the interface of the two systems. And that, of course, has implications in terms of mechanical properties. If you have a lot of voids, if you have a lot of defects, this is what you get, right? You just get a bigger void. And generally, that's not so great, unless you're intending for that. So if you're intending to make these core shell type structures and using and taking advantage of the Kirkendall effect, you can create structures that are hollow like this if you just wait long enough. So recently there was a fabulous publication where they put nickel and platinum together, and people do this a lot to reduce the use of platinum. So they put in a base metal, so it's some inexpensive, abundant metal. They put it in, and then the two, platinum and nickel, will diffuse together, but it goes through this Kirkendall type effect. So whatever structure you started off with, they started off with a cube, they actually get cages, okay? And these cages are made of a platinum nickel alloys that are highly reactive, and they showed that it's a highly reactive. Its catalytic rates beat that of anything that has been produced before. So it pays to know how to engineer and take advantage of the Kirkendall effect. Okay, and so anyway, so that's that. Okay, let me switch back. We are now a week away from your exam 1, so I just like to touch base and describe the exam so that you have ample time to study in a way that's best for you. I've also mentioned already that it will take place during class time, so you just have to show up to class. If you've already made arrangements with us, you will get an email from the lead TA by sometime next Wednesday, okay? So that way, if you don't hear anything from us in terms of a confirmation, then it might not be happening for you, and you should show up on Friday. So please alert us. We've been in contact with those of you that have already made arrangements, and you'll receive another confirmation so that we dot our I's and cross our T's, okay? It's designed for you to be able to take the exam in 55 minutes. In reality, I've designed the exam so that you could really finish it in about 45. And that's to take into account, you know, getting in, settling into your seat, you know, things like that during the transition time as well. So it's really designed so that it should take you about 45 minutes. You'll be provided everything. Okay? You just have to show up with your single-sided 8.5 by 11 handwritten note sheet and your Buck ID. If you don't remember if you don't remember that number, it's on your ID. Just bring your ID with you, okay? You'll be provided everything that you need in terms of the Scantrons, scratch paper. You get 3 sheets, back and front and back, so it's really 6 sheets for computation. So hopefully that's sufficient. We will have more if you need it. We'll be provided constants like Boltzmann constants, the gas constant. You'll be provided any data table that you might possibly need, as well as the periodic table, okay? You're allowed to use your graphic calculator, so you can bring that as well. It's a combination of conceptual and computational questions. It's almost 50-50 in terms of distribution, okay? It'll cover chapters 1 through 5, and it'll be based on what we talked about in lecture, what you've practiced in the homework, and what you've discussed in the worksheets during recitation, okay, for chapters 1 through 5. It will not include chapter 6 because by the time you take the exam next Friday, some of you will have recitation only by Thursday. So those that took it on Tuesday, right, have a little bit more time to prepare. So we're not going to cover chapter 6 for this exam for that reason. So that way you will have time to talk to your TAs, come to office hours, my office hours, TA office hours, recitation, all of that, right, to review anything that you could possibly have questions on, any clarification. I hope that covers it. Any questions? Yeah, Zachary.
What would be the number of questions?
Right now it's hovering at 20. And I've had the TAs practice. And we now have years of compiled data that if they can take the exam in about 20 minutes, then you can complete the exam in about 40, 45, okay? Given your comfort level with computation. So, yes, Kevin?
Just to clarify, we're taking the exams right here in this room.
You show up to class per usual. Bring a pencil, though, because it's Scantron based. So do bring a pencil. Yeah. Yeah, I do try to space everyone out. This room, I think, fits 240 or so, and there's 186 of you. In the front, I think it just can't be avoided that you sit next to each other. You know, I trust that you'll just honor the honor code. Obviously, there's going to be a little bit more space as you go back. So if you happen to sit in the back, I would just ask that you leave space in between you and your neighbor if that's possible. And then we'll move some people around before the exam if needed. Okay? Yeah.
We're allowed to use like graphing calculators, right?
See, graphing calculator confirmed. Anything else? Okay. Be sure to take advantage of office hours next week, okay? And get started on your studying, and definitely let us know if there's any questions. Okay. With that, we'll transition to chapter 6 and get started. We will spend a lot of time talking about mechanical behavior. Actually, while you do that, while you get that started, I'm just going to move around. Hopefully, this will be done by the end of the, it really should take 20 minutes. Don't know what's happening here. All right, let me, you can come up after class as well. I feel like I'm running a cooking show. Okay, focus. Right, mechanical properties. I think this may be review for some of you, given that 58% of the students in this class are mechanical engineering majors, so bear with us. And hopefully what you get out of this is really the tie-in to atomic structure as it relates to mechanical properties and mechanical behavior. And those of you who don't have a mechanical background, this will be new, and so, you know, we'll all learn together. Okay, so I have photos here to motivate you as to why we care, right, about understanding crystal structures and how that leads to microstructure and how that then affects mechanical properties. Certainly, you want different mechanical properties for different applications. It's not always that you want, yeah, you're okay. It's just hydrogen evolution. So it's not always that you need the strongest and the best of everything. Maybe that's not what you want. Maybe sometimes you want materials that will actually degrade over time. You want some mechanical strength, but then you want to also engineer the fade and the degradation of this material over time. And that could be because you don't want a material to exist for a long, indefinite time into the future, right? We don't want plastic existing for a long time. We want that to actually be biodegradable, right? So can we engineer materials that will have certain properties at the beginning and then, you know, fade in a way? So we'll go a little bit into this towards the end of chapter 6 and then also chapter 8 when we talk about failure analysis. But of course, there are obvious applications that one can think of when one is thinking, how do I improve the strength of a material? How do I improve ductility of material? How do I not induce, you know, rupture or, you know, fast fracture, right? And so there are obviously structural applications where we do need that. And then we also want to think about how do we control mechanical properties in materials that we know are strong but are also brittle. They will fracture before they plastically deform, before they permanently deform, right? So we know glass is going to shatter, but can we engineer in a way where it doesn't shatter in your face in a car accident? Okay, something like that. So mechanical properties is absolutely important. And so we talk about mechanical properties in a number of ways. We talk about the stress and strain of a material. We talk about elastic deformation or deformations that are recoverable. How much can you stretch a material or apply force in tension, but then have the material go back to its original structure? And then how do we plastically deform? How do we permanently deform a material and that it doesn't go back? Sometimes we don't want to. You know, it's okay. And sometimes we do. And so there are ways we talk about this. You may be familiar with terms such as stiffness when we talk about a material's modulus, or strength, the yield strength. You know, where is it going to go from elastic deformation to plastic deformation? We're going to talk about ductility. We're going to talk about toughness, the amount of work that it can, energy that it can absorb. We're talking about hardness, resistance to impact, resistance to penetration. Okay, and there's different tests that one can do to quantify all of these values. And then, of course, once we lay down this foundation, we can use it, right? We can use it to actually engineer and control a system, which is the ultimate goal. We want to understand something to the point where we can control it, okay? So this is the overarching curve. You will see this curve again and again if you haven't seen it already. What it does is it relates the stress of a material to the strain. And so I will just draw on this plot and we'll go into great detail all of these terms in the near future, okay? So you can, oops, sorry, already. Oops, I meant to draw that. You can relate the strain of a material, so, you know, elongation of a material, to the stress. And Usually, if you're talking about a metal, we're talking about megapascals, and we're talking all the way to gigapascal, right? We're talking hundreds of megapascal to 2 gigapascals for metals. And so typically, if you've seen those kind of experiments where you stretch in tension, right, you're deforming the system in some sort of way, you're applying some sort of load, and that's newtons per meter squared per that cross-sectional area, okay? So that's your stress and strain. And then at some point, as I've said, your material, you're going to deform, you let it go, it's going to go back. At some point, you apply the load, you let it go, it's not going to go back to where it was before, right? So we talk about strength, right? That's the yield strength, okay? Between the elastic and the plastic region. And you see here on this curve, you can keep on applying that load, and then you'll have what's called an upper yield point and a lower yield point. Sometimes what you'll see in more perfect systems or more ideal is the curve just continues on like this, right? It curves a little bit, and then it just keeps on going. And so the more technical definition for yield strength would be in the community is that you look at your initial length of some material and then its eventual length subtracted by the initial length. So that difference. And we've said, okay, well, if it's about 0.002, that's your yield strength. And so yes, this is strain, and this is stress. Stress is the force that's applied divided by the cross-sectional area, F divided by A. Okay, so let me delete that and be a little bit more. There you go. Okay. So that's where we define the yield strength, because one could argue, where along this curve should you stop? Should you count what the yield strength is? We've just said, okay, if the strain is at 0.002, you extrapolate that, and that's going to be your yield strength. That's just the convention in terms of defining the yield strength and where that curve actually is. Yeah? Yeah, it's a... Yeah, it could deform then, and you could think about braces, right? A good example, well, now we're getting into the discussion of creep and things like that, but yeah, you can absolutely, the rate of which you apply has everything to do with its mechanical behavior. So you can also think about plastic bags. I don't think I have okay, there's a lot. You know what, I'm just turn it down a little bit. It has to cool down anyway. So you can think about silly putty, or even a plastic bag. Okay, here you go. Even polymers, right? I mean, there are chains of polymers in this bag, and if I apply a load, okay, it just tore, but ignore that, right? So it's going for the parts that didn't tear. You could see it had a mechanical response, right? Now if I do this, right, very different mechanical properties depending on the rate of the load that I apply. So the rate of the load, sorry. Yeah, so absolutely, and metals will respond in the same way. So this is not, too slow. You just pull it and then let go. Okay, so let's see, what else? Right. So there can be some recovery. The ultimate strength, or the UTS, or the TS, right, is just the highest point. We'll talk about strain hardening as well. When you work a material, you can actually make it stronger. So we'll talk about that. Necking. So as you mentioned, right, when you apply a load in tension, you're pulling and you're deforming the material overall. And the cross-section is getting thinner and thinner. You can't really see that in the plastic bag demo, but that does actually happen. Okay. Oh, and then there's failure, right? What's the point of failure? Here is the point of failure. So basically, there's nothing. Your material has broken apart, right? So you can't actually continue the measurement, and it can fail slowly, but it could also fail very fast, and that's a rupture. And so that typically happens more so not in metals. Metals tend to not rupture all that much. There's some time for you to deal with the failure. Okay, then we talk about Young's modulus. We'll talk about the relationship of this slope. So in the elastic region, let's say here, so in the elastic region, the slope of this is your Young's modulus. Okay, so we'll talk about Young's modulus and how stiff a material is based on this slope. And then we'll also talk about how tough a material is. And so toughness is just when you integrate. So you take the area under the curve, okay, from 0 to whatever this E is, okay, some E. We'll call that E1, sure. All right, so toughness is just the area under the curve. And then what we've been talking about before is plastic deformation, when something will go back to its usual crystal structure versus when it will not. So those are the two regions that we'll focus on a lot. Oh, and then of course there's ductility as well. So the ductility is just, if you extrapolate this with the same slope times 100, so it's the strain at failure times 100 gives you ductility, which is not on this list. Okay, so that's it. That is how you manipulate this plot and read this plot, the stress strain plot. And we'll go into detail all of this, but when you take a look at a plot like this, these are the things that it can tell you about your material right away. Okay. Okay. Well, we've already talked about this, right, in terms of measuring the force and the displacement. So let's go to that. Here is pictorially what's happening, right? You start with a dog bone, and the way you design your material, you cut into this dog bone so that you can actually clamp your instrument to your material and induce the failure where you want it to where you want it to happen, which is this middle section here. So if you design the dog bone in this way, the fracture will always happen in that region. So you could see pictorially, just graphically, what happens, right? The material elongates from its original shape, and so we talked about the cross-sectional area actually decreasing. But what we're really talking about when we talk about the stress is the force divided by the original cross-sectional area. Okay, so that's the engineering stress. And then at some point, right, it starts to neck. You can see here, and then of course, there's going to be fracture when it actually splits apart when you've applied enough load. And so here's some units. Here's some cartoons that go with the measurements that I've been talking about, right? So you can have both elongation, so that I've just talked about, right? The final length minus what you started with, your L naught. That's the initial length. And so that's just written as delta L naught. Yeah.
How do you find A naught?
Yeah, so that you've already machined out. Yeah, you tell whatever machine make this, with this cross section. So you know from the beginning.
If it was only a test, something they would give this out.
Oh yeah, absolutely. Yeah, you can just take your caliper and just go boop. Okay, or take a ruler, in pi r squared, and that's your cross-sectional area. Okay. Of course, when you're elongating your material in the plane, right? It's actually in the lateral direction. There will actually be shrinkage, and so we can also talk about the difference in the difference in the width as your material is shrinking in the lateral direction while it's being elongated. Okay, so that's also shown here. And we can relate the two, the elongation versus the shrinkage, by the Poisson ratio. Okay, this is just a cartoon, so I'll skip that. Yeah, so the ratio just relates, okay, how much is it going to shrink in the lateral direction versus how much is it going to stretch in the longitudinal direction. So this is lateral. Okay, and that's it. So Young's modulus is just how we talk about stiffness. It's the rise over the run, and that gives you the slope, your Young's modulus. Okay. And because it's in this recoverable regime, we can treat it as sort of Hooke's law. You know, you stretch it, it'll come back. Okay. Right. So a good example is if we're giving a load, some stress that's applied. So here it's 20.7 megapascals, right? And we know the modulus is 207 gigapascal, right? So it's some steel. So then we can calculate the elastic strain in this material. And you just apply the relationship like so. So here it says 20.8, although it really should be 20.7. Sorry about that. And so when you divide it, you could see that you get 0.0001. And it's unitless, right? Because before we said this is just delta L over L naught. So it's just distance divided by distance, which means it should be unitless. Okay? And we can also convert that to a percentage if we multiply by 100, and we get 0.01% elongation for this particular material, okay, for this particular steel. So you can see it's pretty straightforward manipulation. Okay. Let's see. Now we can also then calculate what is the resultant length under stress if you know the starting material. So you've taken your caliper, you've taken your ruler, you know, okay, I start off with 1 meter, and I know the elastic strain. Now I can calculate the stress. So I believe, okay, first of all, this should be in meters, sorry. So if you know, okay, it started off as 1 meter, well, what's the difference, right? So this is 1 meter. And you know the strain, because you just calculated here. So then you can manipulate the equation so that you get that, and you can calculate your delta L. So if you know that L is, delta L is L minus L naught, and you could say, okay, well, this is 1 times 10 to the minus 4 equals L minus 1 meter. Thus, your eventual length is going to be 1.0001 meter. Okay. So if you know the modulus, you can work within the elastic regime pretty well, manipulating all of these values. Okay. It's 11:10. I'm going to end class just a little bit early here because I need to clean all of that up before the next lecture. We'll pick up from here on Monday and continue on chapter 6, okay?